Hello and good afternoon. My name is Adam Warren. I am an honors student here at University of Advancing Technology, majoring in Advancing Computer Science and Robotics and Embedded Systems. My skills include a variety of coding languages, including C++, CSS, JavaScript, HTML, Python, Kali Linux, Arduino, as well as experience in 3D modeling and printing and command prompt interfacing. Now let me ask you a question. Have you ever wondered what exactly is in the air you are currently breathing? Are you located within a trouble spot or looking at your phone, looking at your basic air quality system and wondering is the data accurate? Well, that's where my project comes into play. My project is known as Artificially Intelligent Measurement and Detection, or for short, AIMD. Now, what exactly is AIMD and how does it operate? Spatial correlation and leveraging are both key components to this project. AIMD is a Python-based application used to monitor real-time trouble spots, find any future trouble spots that may come to bear, and reveal to you what form of contaminants, toxins, or pollutants are found within the air, as well as how high they are and why they're so problematic. Now, some of you may be wondering, Adam, how is this different, and what makes this project so special compared to so many other products that are out there in today's world? Well, let's get to the innovation. This program uses a layout of spatial and temporal correlated signals over the air computation to monitor such air emissions. These signals are capable of calculating where the issue is originating from, in turn, literally tracing the problems back to their original source. But the real work, it all begins with data leveraging. From a variety of open data sources obtained, a data fetch is initiated within this program. Now, in addition to the signal correlation, a custom-made server-sent event-based algorithm organizes each individual dataset into autoencoders. This is a big help with calculation and data coverage. Once this algorithm completes the data processing, the signals come into play. Each byte of data is then carefully placed onto these signals, which are carried to certain points all around the globe. The trouble spots are then highlighted onto a dramatic amount of modeling, telling you where these trouble spots are and what contaminants are in the air. Here is a little behind the scenes look of my program and the work I did when I first started constructing it. So as you can see in the opening, I have my libraries all listed here. As you can see, they are fairly extensive to see that this project works to full fruition and there are no aspects missed whatsoever. So to start off, I have Streamlit here to have this project open on a basic web browser tab. Next comes request to pull the incoming data from the individual datasets I have listed within this code. These next four libraries are fairly self-explanatory. JSON processes the incoming data, while these next three initiate the math part, calculating and finding the consistent patterns that may come to bear within the program. These next two are all about graphing, so the data is openly displayed and the person can see the patterns found. These next three are more deep in depth. They're all about machine learning, so that the program can learn from each set and find any patterns that may occur in the future. Here I have the configuration of the web page itself as well as the opening part of the algorithm. And you may have noticed this has been divided into a few functions, so there are no parallax, latency issues, or unnecessary entanglement. So to start off, here I have my distance matrix to enlist each of the locations as well as their precise coordinates, hence the enlistment of latitude and longitude. Here comes my more mathematical aspect, which searches for different aspects within the air quality data, such as molecular weight, temperature, which has been configured to Celsius in my case, and barometric pressure. Here we have our data fetch, which holds our data sources and provides us with active coverage for each source. And now onto the active application. Here I have my basic monitoring tab open with each of the locations listed, data retrieved from each, and yes, it is in military time, but the last time the data was updated. So for simplicity's sake, let's start with something basic. At this point, new data has been retrieved for each of the locations and their patterns analyzed. Any pattern that has a normal outcome resides in the blue, and any one with a higher count resides in the red here. Now let's dive into the whole signal correlation part of the project. This all needs to begin with getting data from a specific location. First, we're going to go into raw data and select, say, Brazil. So I'm going to plug the coordinates in for Brazil. And initiate the data fetch, and we should get the readouts for Brazil, currently anyway. And voila. And here we are provided with the current readouts for particulate matter in the air. Next, we have sulfur dioxide, and we have readout charts for each of them. And finally, to show where the trouble spots are coming from, here we have our mapping system, which is useful for highlighting where the trouble spots are in specific continents around the globe and how high they are. And that concludes the live demonstration of AIMD, as well as a short explanation of its fundamentals. Now keep in mind, I'm always willing to hear any major change that could be added to improve this project, or even the smallest suggestion. And let me tell you, creating a project like this was no simple feat, but if there's one thing I've learned here at UAT, it's a learning experience in the long run. And I truly believe that given enough time and enough research onto the subject, this project could one day be capable of so much more. Thank you for watching and have a nice day.